Hello. This corresponds to chapter 15, sections 1 and 2 out of the Cummins and Kaufman book. And in this chapter, we're going to be looking at our own galaxy, the Milky Way, as the starting point to understand galaxies in general and the whole universe, the structure of the universe. We're going to start with a video from the European Space Agency that is a virtual trip that goes from the center of the galaxy all the way to the outer edge, and then comes back all the way to the center. And we'll start now, I think. Well, that gives us a very good introduction to what we're going to study. You can see that our solar system is somewhere in between, in the middle of the Milky Way galaxy. But then, and it also shows the shape of the Milky Way galaxy. So these questions that are here, numbered 1, 2, and 3, are more or less answered by the video. What is the shape of the Milky Way galaxy? Well, it's kind of a flying saucer seen from the side. Where is our solar system located in the Milky Way? We just saw that it's about somewhere in between the edge of the galaxy and the center. Is the sun moving through the Milky Way galaxy? Well, we're going to learn that indeed it is. And we're going to start with, in section 1, with a debate about what was actually the Milky Way galaxy, whether it was a separated object or the whole universe. And there was a debate about it in 1924. And it was in the 1920s. In the 1924, there were observations by Hubble, not the telescope, but the astronomer, in which he corroborated the fact that there is stuff, objects outside the Milky Way, showing that the Milky Way is just one of many, many, many galaxies. And continuing the study of our skies, people begin to realize that these galaxies tend to group themselves into clusters of galaxies. And these galaxy clusters tend to connect themselves with one another into superclusters. And there were some unexplained topics that led to the introduction of something that we cannot see, that we know that is out there, but we cannot see, and it is known as the dark matter, which interacts with everything gravitationally, but it doesn't produce any light, so it is hard to detect it. Here we have one example of a nice galaxy. In the next chapter, we're going to see the categories of galaxies, different types of galaxies. But this is a nice example that shows you that there is something here at the center. Some call it the nucleus, some people call it the bulge, and then the disk. And this is not the only type. We're going to see that there are some other types, more egg-like shape. And this is a longer list of the things that we're going to see. The Milky Way is composed of billions of stars, and they are bound to each other gravitationally. And we're going to learn about the structure of the Milky Way. Where are we in terms of this structure? And do we have new stars? Yeah, the gas. There's a gas, as we saw in the previous chapters. There's a gas and dust that are producing star formation. And we also have things that we still have to identify. Dark matter is one of those things. And we now know there's a massive black hole at the center of our galaxy. So in the upcoming chapters, we're going to see what are galaxies, what are the structure of galaxies, the clusters, superclusters, and the expansion of the universe. Interesting stuff indeed. We closed this introduction with a schematic diagram of the structure of the Milky Way. This is, of course, is not the Milky Way. We have never left the Milky Way to take such a picture, but we have seen other galaxies that we believe have a similar structure. So we have basically a disk, we have a bulge, and all of this is surrounded by, not by stars, but by clusters, spherical clusters of stars. And we are somewhere here between the edge and the center, almost exactly at midway between the two. So this looks kind of like a Mexican sombrero or like a flying saucer. And there's good news. There's a bar at the center of the galaxy, the galaxy bar. No, just kidding. This galaxy bar, by the way, is in Athens, in Greece, but we're talking about a different type of bar. That other bar is this bar, the one that is at the center of the galaxy, and it is basically a collection of stars that somehow are disconnected from the rest of the stars. All the action happens here. New stars are born and die here. But these guys are very old stars that have their own motion inside. They never leave the bar, and so they can be considered as something outside the rest of the galaxy. So this is what is known as the bar. There are some galaxies that have a bar and some galaxies that don't have a bar. We're going to see that classification later on, the so-called Hubble classification of galaxies. And what we know is that our galaxy has two arms that are major plus several other arms. So depends on how you classify them. You can say that it's anywhere between 2 and 6, I suppose. And we know of this by means of very interesting analysis of the radio waves that are produced by the gas that is moving on those arms. Well, here are the questions that you would have answered in class. At this point, I recommend that you pause this narration and answer the questions. I'm not going to give you the answers. You can go back and check the text, study them, and we're going to continue now with section 2. I mean, section 1. This is the beginning. Yeah, that was the introduction. In section 1, it's a little bit of history. In the 1700s, people didn't know what to think of our galaxy. They just didn't have the resolution. Remember that all of this began with the study of the skies with telescopes. It started with Galileo in the 1600s. Well, we're about 100 years later, and there were very nice telescopes already built, but people began looking at things that didn't look like stars. They looked more like clouds. So they called them the nebulous stars. And we're talking about the 1780s. And there were some drawings about the so-called nebulous stars. And this fit more or less with what this philosopher was arguing. He was saying that that we were just an island in the whole universe, and that this island was kind of a universe. It was an island universe. So, of course, philosophy says nothing except ideas. The proof is in the observations. So, later on in the 1840s, about 100 years later, a person that later became Lord Rosse built a powerful telescope, and he began looking at those nebulous stars, and indeed he identified them. It was very interesting. In the next slide, we're going to see something very interesting. An interesting observation from Lord Rosse. This is the telescope that he built. Look at the size of this monster. He built it in 1845. The guy had a lot of money, so that's why he didn't hesitate in doing it. It was the most powerful telescope for many years. But look at what he was competing against. He was competing against what Herschel had been using like 40, 50 years before. This is nothing compared to the other one. But anyway, Lord Rosse began using his piece of resistance to observe the universe. And this was before the invention of photography. So he had to make sketches, and the sketches looked like this. And now we know that indeed he was looking at this. So you can see the resemblance. And the question that he brought up for discussion was, is this part of our own Milky Way, or is this outside our own Milky Way? Well, the question was, are we the whole universe, or are there any other universes out there, or the universe contains more galaxies like ours? Well, in the 1920s, there was a discussion. It was a formal discussion between these two guys, Shapley and Curtis, and it was held at the National Academy of Sciences about whether we were the only game in town or not. Shapley, here on the left, used to say that that the nebula were small objects sprinkled on our own galaxy. So for him, our galaxy was the whole universe. And Curtis, here on the right, said that no, those guys are separate nebula that they are away from outside our Milky Way. So this debate didn't have a conclusion because they didn't have enough information. It was just more philosophical than anything else. But not too long after that, Hubble, photograph here, down here, took a picture. It is a long story, but let me summarize it as follows. He took a picture of Andromeda Nebula, and there he found something that he thought that it was a nova, but it was not, because it was a recurrent. It was increasing in magnitude in a periodic way. So it was a Cepheid, and turns out that at the time there was a study being conducted that related the period of oscillation of Cepheids with the luminosity. And turns out that by knowing the period, you could find the absolute luminosity of the object. And if you have the absolute brightness and the apparent brightness, of course, you can calculate the distance. So Hubble did that for what he had seen in this Andromeda Nebula, and found the distance of those objects, and it turned out that the distance was just too large to be inside of our galaxy. So he concluded that those objects were in a different galaxy outside our own, and that settled the debate. But let us look at the relationship between this Cepheid, the variability of the Cepheid, and its absolute brightness. It was this type of studies was performed by the bunch of ladies that were hired by different observatories to analyze photographs. They were taking hundreds and hundreds of photographs, and in particular, Henrietta-Leavitt was the one that did meticulous classification of the period and the brightness, the relationship. And in the next video, we're going to see how all of this happened.
We see the night sky as a vast array of thousands of luminous objects that appear as tiny dots. Among them, there are several nebulous patches called galaxies. How far away are these galaxies? Are these objects scattered among the stars just as small as they appear to the naked eye? Or are they larger? How far away from us are they? And how can we tell? The answers to these questions came with a crucial discovery, but it was not made by a great professor or famous scientist, but by a modest, hard-working astronomer, the remarkable Miss Henrietta-Leavitt.
I was working at Harvard College Observatory as one of many computers, working for minimum wage and sorting through piles of data of thousands upon thousands of stars. For centuries, sailors from the southern hemisphere spoke of two fuzzy patches in the sky that looked like detached parts of the Milky Way. These became known as the Small and Large Magellanic Clouds. They could not be seen from the northern hemisphere, but we had many good photographs of the clouds taken from our observatory in Peru. I spent many years measuring and studying the stars in the Small Magellanic Cloud. I soon discovered that the brightness of many of these stars changed periodically. When a star was brighter, its image on the photographic plate looked bigger. When it faded, it looked smaller. These are called variables. Day after day, month after month, year after year, I searched for those variables, measuring their brightness and computing their periods. And then, a pattern started to emerge. I noticed a remarkable relation between the brightness of some of these variables and their periods. The brighter the variables had longer periods. The fainter variables had shorter ones. The relationship was unmistakable. I was able to do precise measurements for 53 such stars. Then I made a graph. On one axis, I plotted the length of their periods, and on the other, their maximum brightness. A precise mathematical fit emerged, showing what became known as the Perio-Luminosity relation, the laws obeyed by these stars. These stars became known as Cephid variables, or Cephids for short, as we first found them in the constellation Cepheus. Relationships like this don't happen by accident. Rather, they must reflect something deep about the true nature of these stars. I hoped that systematic studies of these variables would shed more light on this issue, but I had no time for that. Others would have to take up that task.
Indeed, they did. Henrietta might have continued her work had she not been held back by her poor health. She died several years later after battling a long illness. But the results of her labor lived on. Astronomers quickly realized the importance of Henrietta's discovery. Cepheid variables are easy to spot, and they have been found all over the sky. Einar Hertzsprung realized that they can be used as light beacons to measure distances. By comparing Henrietta stars to Cepheids that are nearby, Hertzsprung was able to estimate the distance to the Small Magellanic Cloud. Harlow Shapley used Henrietta's Perio-Luminosity relation to estimate the size of our galaxy. And Edwin Hubble used this relation to measure how far away other galaxies are from us. He found that the universe is expanding. Wendy Friedman led a team of astronomers that found out just how quickly it is expanding. Using Henrietta's Perio-Luminosity law, they were able to measure the distances to galaxies that are 66 million light-years away. Henrietta's discovery became one of the foundations of modern cosmology.
Miss Leavitt had the happy faculty of appreciating all that was worthy and lovable in others, and was possessed of a nature so full of sunshine that, to her, all of life became beautiful and full of meaning.
So here we have the relationship that he came up with, and this is presented in a log scale, so it looks more like a straight line. And you can see that this is the period of oscillation of the brightness of oscillation of the brightness in those Cepheids, and in days. And this is the maximum luminosity they achieve, and you can see that it looks more like a straight line here. So just by counting how many days it takes for the luminosity to go back to its maximum, you can estimate the luminosity, the absolute luminosity. And if you know the apparent luminosity, which you do, then you can estimate the distance. So using this possibility, in 1924, Edwin Hubble calculated that the object that he was looking at in the Messier 31 galaxy was 2.2 million light years away. So showing that this galaxy is not inside of our Milky Way, but it's a separate galaxy, and with this putting to rest the debate between Shapley and Curtis. And here we're going to see that how the views of Hubble, the discovery of Hubble, changed the way that we think about the universe. By using this methodology of finding distances, he managed to find another relationship that is very interesting.
Less than a century ago, the bright arc of our Milky Way was thought to contain all the stars in the universe. But astronomers were perplexed by a cigar-shaped object in the autumn sky called the Andromeda Nebula. Some astronomers thought it was another galaxy like our Milky Way. It too had a flattened disk shape. But how far away was it? In the early 1920s, astronomer Edwin Hubble photographed the nebula in detail. He found a pulsating star hidden deep in one of its spiral arms. Edwin Hubble used it to calculate the distance to the Andromeda Nebula. This showed it was far beyond our Milky Way. Andromeda, in fact, was really a separate galaxy. The Hubble Space Telescope has recently observed this star as a tribute to the landmark discovery.
These are the questions you would have answered in class. I ask you again to pause and answer the questions. You can check your answers by going back to the text of the previous slides. Well, in looking at our galaxy, people wanted to decide what was the structure of our galaxy, if there was any. And the first time they did that systematically was done by Herschel in the 1780s, and he did something that was obvious, but he got the wrong answer. And the way he did it was to partition the sky in different sections and count how many stars you could see. So he divided the sky into 683 regions, and he said, oh, well, in this region we have so many, I see. In this other region I see so many. And he kept on counting as he went around, and he found that all of the regions have roughly the same amount, the same density of stars. When he concluded, well, we are at the center of the galaxy, which is very comforting by thinking that we are at the center of the whole thing. But anyway, he was wrong, of course. And what was the problem? Well, the problem is that with the technology that he had, you cannot see everything because of the dust that the galaxy has. So you can see just up to some distance away, and if you count around in a sphere, you're going to see roughly the same density everywhere. So you reach the wrong conclusion. But turns out that now we have a better idea of how to do this, and turns out that we are 26,000 light years from the galaxy center, which is interesting because we are almost at the center between the center of the galaxy and the edge of the galaxy. So that distance is about, in other words, the radius is about 50,000 light years. So we are almost at the center. And we have here these things that are floating around there are the ones that gave us the clue about where we are with respect to the center. In section 2, Cepheid variables are helping us to locate the center. Again, the dust that we have all around absorbs a lot of light and doesn't allow us to see the correct structure of the Milky Way. So Shapley, in 1917, he used the Perio-Luminosity relationship to find the distance to 93 globular clusters in the sky. Because of the dust along the disk, it was absorbing a lot of light. It was much better to look above the disk and look at those clusters that are above and below the disk. We have here these clusters, and they are not single stars. They are more than 1 million stars in the disk of the galaxy are here, and clearly seen are those collection of stars that form a sphere. So Shapley, by looking at where these guys were, where the globular clusters were, he's seeing that they are more or less around the same distance away from us. He concluded that they were held in place by something there, and consequently he said, well, this got to be the center of the Milky Way. So it was a conjecture. He didn't have enough information to deduce that, but nevertheless he concluded that the globular clusters that orbit out there are near the center of the Milky Way, which means that the center of the Milky Way was in Sagittarius. And now we know that there's a huge, humongous black hole there. Again, more questions. These are the questions you would answer, and you would have answered in class. I ask you again to pause and answer. And I believe this completes sections 1 and 2.